Hello. In this video, we will talk about one of the operations on sets. In the last video, we talked about intersection of sets, union of sets, and in this video, we will talk about another operations on sets, and that is the operation of intersection. Now, intersection of two sets is nothing but an operation just like the operation of addition or just like the operation of multiplication. But remember that in this case, our elements of the set are not real numbers. Our elements of the set are not natural numbers. Our elements of the set are not integers. Our elements of the set are not rational numbers or any other object. In our case, our collection consists of sets themselves. Okay, so intersection is an operation on a collection of sets. So what is the definition of intersection of sets? Here it is. That's given two sets A and B, then the intersection of A and B is that set which consists of all those elements that belong to both sets A and B. ये definition मुझे ये बताती है अगर मेरे पास दो सेट्स है तब उनके इंटरसेक्शन में वो एलिमेंट्स होंगे जो एलिमेंट्स उन दोनों सेट्स को बिलोंग करेंगे. मतलब हमारे इंटरसेक्शन में वो एलिमेंट आएंगे जो एलिमेंट दोनों सेटों को A एंड B को बिलोंग करे. It will not contain those elements which belong to just one of the sets. यहां पे हमें इस डेफिनेशन में हमें और यूनियन की डेफिनेशन में हमें एक फर्क जरूर महसूस करनी चाहिए. वो ये कि in case of union we had here or, but in case of this intersection there is no or, there is and this and is very special. It says us that simply our intersection in set builder notation we write intersection of two sets this way, and it says us that intersection of A and B is that set which consists of all the elements X such that X must have this property. What property? X must belong to A and X also must belong to B. Now there is another way to visualize sets and their operations as well, and Venn diagrams is one of the ways to visualize sets. I have included here the Venn diagram of intersection of two sets. Suppose that my universal set, given universal set is represented by this rectangle, and my given two sets A and B are represented by these circles, which are unfortunately not perfect circles because I am very bad at drawing. So what does this say? We know by definition our intersection consists of the common elements. It means that if we have two sets and they have some common, then when diagrammatically, visually, they must overlap. So here it is. I'm assuming that A and B have some elements in common. That's why they are overlapping here. And we represent intersection of two sets if they have some elements in common this way. By this intersection is represented by this diagram. And this diagram is called a Venn diagram. Now, I have some examples so that we will be able to grasp the meat of the concept of intersection well. Here is my first example, and my first example consists of two sets. One set is the set A, and it consists of the elements 1, 7, 2, and 8. And my second set B is the set which consists of the elements 7, 13, and 4. Now, I want to know what is the intersection of A and B. Obviously, I will take the help of the definition of intersection of two sets. Now, let's recall the definition of the intersection of two sets. It says us that if I have two sets A and B, then their intersection is defined as that set which consists of those elements which belong to both of the given sets A and B. So, if I apply this definition to this particular example, let's see what we will get. Now, intersection of two sets says us that our intersection of two sets will be consisting of all those elements which have the property that it must belong to both of the sets. So let us see, is I have done this, and my intersection is the singleton set, and it consists of the single element 7. Why 7? Why not other elements? Because by definition, my intersection consists of the common elements. So let's see which of the elements in these two sets are common. 1 is here, but 1 is not here. It means that 1 is not going to land in our A intersection B. Okay, because in our intersection we have to include only the common elements, and 1 is obviously not in both of the sets. Means that 1 will not be included in A intersection B. Okay, 7 is here. Is 7 here? Obviously it is here, because now 7 is here and 7 is also in this set B. That's why I have included 7 in A intersection B. Okay, now similarly 2 is in this set A. Now is this 2 also in the set B? Obviously not. Means that 2 will not belong our A intersection B. Similarly 8 is 8 here anywhere? Nowhere. It is not present in the set B. So means that A will not be included in the set A intersection B. Similarly, I will check for these two guys as well. Is 13 is here? Is 13 also in this set? Obviously not. Means that 13 will not belong to our A intersection B. Is 4 in the set A? Obviously it is in our set B, but 4 does not belong to our set A. Means that 4 will also not be included in our A intersection B. So here is the example, and their intersection, and the intersection of A and B is the singleton set, which consists the only element, that is 7. Now let's see another example. In the second example, my first set contains the elements A, E, I, O, U, and the second set B consists of the elements A, B, C, D, I, G, H. Now if I ask you what is their intersection, now you will apply obviously the definition of intersection, and its definition is that A intersection B will consist of all those elements which will belong to both of them. So let's apply our definition to this very example. Now A is here. I will include A in our intersection if A also belongs to B. Now let's see. A is here. Obviously A is also in my set B. It means that A is going to be an element of my intersection A intersection B. Similarly, is E. Obviously E is in our set A. Is E also present in set B? Obviously it is nowhere. Means that E is not going to land in our A intersection B. Similarly, I can check for each of these elements, and I will pick up only those and put them in the collection of A intersection B, which are common to both of them. And here it is. These two sets have only 2 elements in common, and those 2 elements are A and I. Means that our intersection is the set which contains 2 elements, A and I. Here is another a bit interesting example of intersection of 2 sets. In this example, my set, this example actually will try to answer the question why there is empty set in set theory, or in general in mathematics. Why we need, or is there any need, or do we anywhere encounter empty sets? This is the example that will answer this question. Now consider the example. I have a set A which consists of these elements. I have another set which consists of these elements, and my job is to find their intersection. Now by definition, intersection includes those elements which are common to both of the given sets. So let's see what is common between A and B. Now here is A, my set A, and it consists of the element 1. Is 1 in the set B? Obviously not. Means that my intersection will not include 1. Is 3 in the set B? Obviously not. Means that by definition, my intersection will not include 3 as its element. Is 5 in the set B? Obviously not. Means that 5 is also not going to land in my intersection. Similarly, you can see yourself that these two sets have nothing in common. Now, mathematicians are very, you can say, clever. They even name things which apparently seem nothing. And here they say because A intersection B is defined for any two sets. So what is this set? And mathematicians called this set as the empty set or the null set or the void set. This is an example which forces us to accept a set which contains nothing, and we call such a set as the empty set. Now, the job of the empty set in set theory is analogous to the job of zero, which you are familiar with. It plays the same role, the role played by zero in the set of integers, the role played by zero in the set of real numbers, the role played by zero in the set of rational numbers. Here, in set theory, the role of zero is played by the empty set. Hope this will convey some of the message to you. Thanks a lot. Thanks.